In computer vision, blob detection methods are aimed at detecting regions in a digital image that differ in properties, such as brightness or color, compared to surrounding regions. Informally, a blob is a region of an image in which some properties are constant or approximately constant. All the points in a blob can be considered in some sense to be similar to each other. Given some property of interest expressed as a function of position on the image, there are two main classes of blob detectors: differential methods, which are based on derivatives of the function with respect to position, and methods based on local extrema, which are based on finding the local maxima and minima of the function. With the more recent terminology used in the field, these detectors can also be referred to as interest point operators, or alternatively interest region operators. There are several motivations for studying and developing blob detectors. One main reason is to provide complementary information about regions, which is not obtained from edge detectors or corner detectors. In early work in the area, blob detection was used to obtain regions of interest for further processing. These regions could signal the presence of objects or parts of objects in the image domain with application to object recognition and/or object tracking. In other domains, such as histogram analysis, blob descriptors can also be used for peak detection with application to segmentation. Another common use of blob descriptors is as main primitives for texture analysis and texture recognition. In more recent work, blob descriptors have found increasingly popular use as interest points for wide baseline stereo matching and to signal the presence of informative image features for appearance-based object recognition based on local image statistics. There is also the related notion of ridge detection to signal the presence of elongated objects. The Laplacian of Gaussian, one of the first and also most common blob detectors, is based on the Laplacian of the Gaussian. Given an input image, this image is convolved by a Gaussian kernel at a certain scale to give a scale space representation. Then, the result of applying the Laplacian operator is computed, which usually results in strong positive responses for dark blobs of extent and strong negative responses for bright blobs of similar size. A main problem when applying this operator at a single scale, however, is that the operator response is strongly dependent on the relationship between the size of the blob structures in the image domain and the size of the Gaussian kernel used for pre-smoothing. In order to automatically capture blobs of different size in the image domain, a multiscale approach is therefore necessary. A straightforward way to obtain a multiscale blob detector with automatic scale selection is to consider the scale normalized Laplacian operator, and to detect scale space maxima minima, that are points that are simultaneously local maxima minima of with respect to both space and scale. Thus, given a discrete two-dimensional input image, a three-dimensional discrete scale space volume is computed and a point is regarded as a bright blob if the value at this point is greater than the value in all its 26 neighbors. Thus, simultaneous selection of interest points and scales is performed according to. Note that this notion of blob provides a concise and mathematically precise operational definition of the notion of blob, which directly leads to an efficient and robust algorithm for blob detection. Some basic properties of blobs defined from scale space maxima of the normalized Laplacian operator are that the responses are covariant with translations, rotations and rescalings in the image domain. Thus, if a scale space maximum is assumed at a point, then under a rescaling of the image by a scale factor, there will be a scale space maximum in the rescaled image. This in practice highly useful property implies that besides the specific topic of Laplacian blob detection, local maxima minima of the scale normalized Laplacian are also used for scale selection in other contexts, such as in corner detection, scale adaptive feature tracking, in the scale invariant feature transform, as well as other image descriptors for image matching and object recognition. The scale selection properties of the Laplacian operator and other closely scale space interest point detectors are analyzed in detail in. It is shown that there exist other scale space interest point detectors, such as the determinant of the Hessian operator, that perform better than Laplacian operator or its difference of Gaussian's approximation for image-based matching using local SIF-like image descriptors. The difference of Gaussian's approach, from the fact that the scale space representation satisfies the diffusion equation. it follows that the Laplacian of the Gaussian operator can also be computed as the limit case of the difference between two Gaussian smoothed images. In the computer vision literature, this approach is referred to as the difference of Gaussians approach. Besides minor technicalities, however, this operator is in essence similar to the Laplacian and can be seen as an approximation of the Laplacian operator. In a similar fashion as for the Laplacian blob detector, blobs can be detected from scale space extrema of differences of Gaussians. See Lindbergh for the explicit relation between the difference of Gaussian operator and the scale normalized Laplacian operator. This approach is for instance used in the scale invariant feature transform algorithm. See Low. The determinant of the Hessian, by considering the scale normalized determinant of the Hessian, also referred to as the Munda-Ampere operator, where denotes the Hessian matrix of and then detecting scale space maxima of this operator, one obtains another straightforward differential blob detector with automatic scale selection which also responds to saddles. The blob points and scales are also defined from an operational differential geometric definitions that leads to blob descriptors that are covariant with translations, rotations and rescalings in the image domain. In terms of scale selection, blobs defined from scale space extrema of the determinant of the Hessian also have slightly better scale selection properties under non-Euclidean affine transformations than the more commonly used Laplacian operator. In simplified form, the scale normalized determinant of the Hessian computed from Haar wavelets is used as the basic interest point operator and the surf descriptor for image matching and object recognition. A detailed analysis of the selection properties of the determinant of the Hessian operator and other closely scale space interest point detectors is given in. In it is shown that the determinant of the Hessian operator performs significantly better than the Laplacian operator or its difference of Gaussians approximation for image-based matching using local SIF-like image descriptors. The hybrid Laplacian and determinant of the Hessian operator, a hybrid operator between the Laplacian and the determinant of the Hessian blob detectors, has also been proposed, where spatial selection is done by the determinant of the Hessian and scale selection is performed with the scale normalized Laplacian. This operator has been used for image matching, object recognition as well as texture analysis. Affine adapted differential blob detectors, the blob descriptors obtained from these blob detectors with automatic scale selection are invariant to translations, rotations and uniform rescalings in the spatial domain. The images that constitute the input to a computer vision system are, however, also subject to perspective distortions. To obtain blob descriptors that are more robust to perspective transformations, a natural approach is to devise a blob detector that is invariant to affine transformations. In practice, affine invariant interest points can be obtained by applying affine shape adaptation to a blob descriptor, where the shape of the smoothing kernel is iteratively warped to match the local image structure around the blob, or equivalently a local image patch is iteratively warped while the shape of the smoothing kernel remains rotationally symmetric. In this way, we can define affine adapted versions of the Laplacian difference of Gaussian operator, the determinant of the Hessian and the Hessian Laplace operator. Gray-level blobs, gray-level blob trees and scale space blobs. A natural approach to detect blobs is to associate a bright blob with each local maximum in the intensity landscape. A main problem with such an approach, however, is that local extrema are very sensitive to noise. To address this problem, Lindbergh studied the problem of detecting local maxima with extent at multiple scales in scale space. A region with spatial extent defined from a watershed analogy was associated with each local maximum, as well a local contrast defined from a so-called delimiting saddle point. A local extremum with extent defined in this way was referred to as a gray-level blob. Moreover, by proceeding with the watershed analogy beyond the delimiting saddle point, a gray-level blob tree was defined to capture the nested topological structure of level sets in the intensity landscape, in a way that is invariant to affine deformations in the image domain and monotone intensity transformations. By studying how these structures evolve with increasing scales, the notion of scale space blobs was introduced. Beyond local contrast and extent, these scale space blobs also measured how stable image structures are in scale space, by measuring their scale space lifetime. it was proposed that regions of interest and scale descriptors obtained in this way, with associated scale levels defined from the scales at which normalized measures of blob strength assumed their maxima over scales could be used for guiding other early visual processing. An early prototype of simplified vision systems was developed where such regions of interest and scale descriptors were used for directing the focus of attention of an active vision system. While the specific technique that was used in these prototypes can be substantially improved with the current knowledge in computer vision, the overall general approach is still valid, for example in the way that local extrema over scales of the scale-normalized Laplacian operator are nowadays used for providing scale information to other visual processes. Lindbergh's watershed-based gray-level blob detection algorithm for the purpose of detecting gray-level blobs from a watershed analogy. Lindbergh developed an algorithm based on pre-sorting the pixels, alternatively connected regions having the same intensity, in decreasing order of the intensity values. Then, comparisons were made between nearest neighbors of either pixels or connected regions. For simplicity, let us consider the case of detecting bright gray-level blobs and let the notation higher neighbor stand for neighbor pixel having a higher gray-level value. Then, at any stage in the algorithm is based on the following classification rules: if a region has no higher neighbor, then it is a local maximum and will be the seed of a blob. Else, if it has at least one higher neighbor, which is background, then it cannot be part of any blob and must be background. Else, if it has more than one higher neighbor and if those higher neighbors are parts of different blobs, then it cannot be a part of any blob, and must be background. Else, it has one or more higher neighbors, which are all parts of the same blob. Then, it must also be a part of that blob. Compared to other watershed methods, the flooding in this algorithm stops once the intensity level falls below the intensity value of the so-called delimiting saddle point associated with the local maximum. However, it is rather straightforward to extend this approach to other types of watershed constructions. For example, by proceeding beyond the first delimiting saddle point a gray-level blob tree can be constructed. Moreover, the gray-level blob detection method was embedded in a scale space representation and performed at all levels of scale, resulting in a representation called the scale space primal sketch. This algorithm with its applications in computer vision is described in more detail in Lindbergh's thesis as well as the monograph on scale space theory partially based on that work. Earlier presentations of this algorithm can also be found in more detailed treatments of applications of gray-level blob detection and the scale space primal sketch to computer vision and medical image analysis are given in Maximally Stable Extremum Regions. Matters al. were interested in defining image descriptors that are robust under perspective transformations. They studied level sets in the intensity landscape and measured how stable these were along the intensity dimension. Based on this idea, they defined a notion of maximally stable extremum regions and showed how these image descriptors can be used as image features for stereo matching. There are close relations between this notion and the above-mentioned notion of gray-level blob tree. The maximally stable extremum regions can be seen as making a specific subset of the gray-level blob tree explicit for further processing. See also, blob extraction, corner detection, affine shape adaptation, scale space, ridge detection, interest point detection, feature detection, Harris affine, Hessian affine, PCBR. References: Christopher Evans. Notes on the OpenSurf library. H. Bay, T. Tutelaars and L. Van Jewel. Surf, Speeded Up Robust Features. Proceedings of the 9th European Conference on Computer Vision, Springer LNCS Volume 3951, Part 1 pages 404 417. L. Brisa and T. Lindbergh. Feature Tracking with Automatic Selection of Spatial Scales. Computer Vision and Image Understanding 71, pages 385 392 doi, 10.1006/CVIU. 1998.0650. CS1 Maintenance, Extra Text, T. Lindbergh. Detecting Salient Blob-like Image Structures in Their Scales with a Scale Space Primal Sketch, a Method for Focus of Attention. International Journal of Computer Vision 11, pages 283 Euro 318 doi, 10.1007/BF01469346. CS1 Maintenance, Extra Text, T. Lindberg. Scale Space Theory in Computer Vision. Springer. ISBN 0-7923-9418-6. T. Lindberg. Feature Detection with Automatic Scale Selection. International Journal of Computer Vision 30, pages 77 Euro 116 doi, 10.1023 per hour, 1,008,045,108,935. CS1 Maintenance, Extra Text, T. Lindberg and J. Garding. Shape-adapted smoothing and estimation of 3D depth cues from affine distortions of local 2D structure. Image and Vision Computing 15, pages 415 Euro 434 doi, 10.1016 per second 0262-8856, 97, 01144X. CS1 Maintenance, Extra Text, T. Lindberg. Scale Space. Encyclopedia of Computer Science and Engineering, John Wiley & Sons 4, 2495 Euro 2504. doi, 10.1002/9780470,050,118 x 609. ISBN 0-470-05011X. T. Lindberg. Scale Invariant Feature Transform. Scalarpedia, 7, 5, 10491. doi, 10.4249/Scalarpedia 10491. D. G. Lowe. Distinctive Image Features from Scale Invariant K-Points. International Journal of Computer Vision 60, pages 91 Euro 110 doi, 10.1023 per byte, BISI. 000029664.99615.94. CS1 Maintenance, Extra Text, J. Matters, O. Chum, M. Urban and TPAJDLA. Robust Y-baseline stereo from maximally stable extremum regions. British Machine Vision Conference pages 384 Euro 393. K. Michael Larcock, K. and C. Schmidt. Scale and Affine Invariant Interest Point Detectors. International Journal of Computer Vision 60, pages 63 Euro 86 doi, 10.1023 per byte, BISI. 000027790.02288F2. CS1 Maintenance, Extra Text,